Hello, this is Dr. Strickland. In this video, we will conclude our investigation of the Diels-Alder reaction. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the more difficult things we will do together in class. When we talked about the reactions of alkenes, we classified them as regioselective, stereoselective, and stereospecific, depending on exactly what their pieces and parts looked like. And sometimes we had carbocation intermediates to talk about, sometimes syn addition, sometimes anti-addition. It turns out that you can do the same things with the reactions of conjugated dienes. So we're going to look at a special case where you have an unsymmetrical diene and an unsymmetrical dienophile. And what that means is that this double bond and this double bond are different somehow. The one on the right has this methoxy group attached to it. And then we've got an unsymmetrical dienophile, but we're looking at this vinylic carbon and that vinylic carbon, and the things that are attached to them are different. In the case where you have an unsymmetrical diene and an unsymmetrical dienophile, the Diels-Alder reaction will be regioselective. If even one of them is symmetrical, it's not. But in this case, I wanted you to see why it is that this one turns out to be the major product and this one isn't formed. Okay, well, what we're going to do is we're going to look at the resonance contributors for this conjugated diene and then its dienophile. So you know that when you're looking for a system of delocalized electrons, mostly you're looking for atoms in a row that have either sp2 or sp hybridization. Could be a carbocation, something that's got p orbitals that are available to move around. You can have down one end, you can have an sp3 that has non-bonding electrons attached. And if you do, then it's got to start here because we can't move towards an sp3 atom, but we certainly can move away from it. So in this case, we're not going to draw all of the possible resonance contributors. I'm only going to draw the one that involves these three electron movements. I'm not going to stop at the one in the middle because what I want you to see is what happens to the charges, the formal charges. Now, all the atoms are still in the same place. Wherever it was that you left them, they're still there. All that moved, sorry, that's a 2. All that moved was the electrons. So these non-bonding electrons turn into a pi bond. This pi bond comes around here, becomes a pi bond at the adjacent position. And then these electrons of the pi bond come up here to be a non-bonding pair of electrons there. If you go through and calculate the formal charges, and I would suggest that you do to make sure that you remember how to do it, you'll find that you've got a negative charge here and a positive charge here. And that makes sense because if this one has a net 0, then if I've got one charge, I've got 2 charges. Okay, so here we've got 4 sp2 hybridized atoms in a row, and we're going to move towards the more electronegative one. So that's movement like this. And then what does our second resonance contributor look like? Okay, atoms all still in the same places. None of them move because this is a resonance contributor. I apologize, that's not supposed to be there. And now instead of having 2 pair of non-bonding electrons on that oxygen, I've got 3. And I've got only 3 bonds to that carbon, so it's got an incomplete octet. Positive charge here, and oxygen with 3 non-bonding pairs and one covalent bond is a negative. Okay, so these are the 2 resonance contributors for both of these. What I want to do is I want to look at the atoms that are down at the bottom here. So here you see how we've got a negative charge there, and we've got a positive charge here. I'm looking for the atoms in this conjugated system of the conjugated diene where do I have a charge on one of those? And with the dienophile, with the 2 vinylic carbons, where do I have a charge? Because those charges are opposite. And I know that the bond, one of the sigma bonds is going to form between these 2 carbons. And that tells me that the correct orientation was this one. Okay, so I'm just going to draw them in skeletal structure. But so when I have the electron movement here, that's why we get this constitutional isomer of the product, but not that one. Okay, we need to work that through with some examples if that doesn't quite stick yet, because there's a lot to it. All right, let's move from regioselectivity to stereoselectivity. It turns out that the Diels-Alder reaction is stereoselective because it's a thin addition. And that means that this thing can come in from the top, from, like above this conjugated diene, if you kind of look at it like hovering above it on the paper, like that, or if it were to come in below. So if it were to come in from above, the product would look like this, because we would form these 2 new bonds, and these 2 pieces are going to come in on the same side. They're both going to be above because these 2 bonds are formed on the same side. So because it's a thin addition, they can either have 2 up bonds or 2 down bonds. And then we've got another one up here. All right, so let's give this a little, maybe something for you to hang on to. Okay, let's say that when we've got our dienophile set up, let's say that the things that are on the right are going to end up on up bonds or down bonds in the other one. Okay, but in up bonds in the first one, down bonds in the second one. So if we're looking here, things that are on the right are those 2 things. So this one would be the solid wedge goes to that guy. The solid wedge goes to the hydrogen. And the dashed wedge to the methyl. So let's put the hydrogens in here into these other ones also, just so it's complete. And then in the other one, because it came in from the bottom, it will be the other way. So this one would be down, and then the methyl group would be up, and the hydrogen would be down. All right, let's put them in up here as well. So it's stereoselective because it's thin. These 2 bonds are formed on the same face of the conjugated diene, either both from above or both from underneath, whether you're talking about cis or trans. So it's stereoselective because it's thin, but you can also see that it's stereospecific, because if we start with the cis dienophile here versus the trans dienophile there, these 2 stereoisomers are not the same as those 2 stereoisomers. So it's also stereospecific in this case. All right, one other thing I want you to be able to do is to go backwards and look at a product that has a 6-membered ring in it and go, what diene and what dienophile should have been used to synthesize each of these? So I'm going to use that open arrow that indicates walking backwards one step. And so now I'm going to do some color coding. All right, let's look at the first one. the new six-membered ring that's formed has to have a double bond in it. That means the conjugated diene had to have been here. And these are the two new bonds. And these guys were part of the dienophile. So walking backwards, that means that these four atoms were from the conjugated diene. And those two of the new six-membered ring had to have been part of this cyclohexanone to begin with. That and that. That and that. So there's your diene and your dienophile. All right, what about something fancier? Well, if you have to choose, then actually you can do this side as the diene and this side is the dienophile, or vice versa. But I think we'll do the left-hand side from the diene. So this, the new six-membered ring is this one right here. These are the two new bonds that were formed. These two must have come from the dienophile. So the dienophile had one more pi bond than it does right now. So that means that my dienophile must have been an alkyne. In fact, it must have been 2-butyne. These were the two atoms of the dienophile. And then my conjugated diene must have been this, because there's that one that's poking up, right? There's those two and these two. All right, so that's the basic story on regioselectivity, stereoselectivity, and the Diels-Alder reaction. If you have questions, please send them to me.